Check this out. You see this water evaporating? Seems simple enough, but why does it evaporate? This has actually long been a mystery of science. Conventional wisdom says it's because heat from the sun's rays heat up the water and cause it to evaporate. And yes, that's true, but it's only part of the story. There's a missing piece to our understanding, but scientists at MIT just discovered a new phenomenon they're calling the photomolecular effect. They discovered that photons from the sun can evaporate water directly and not by heating it. Now, this can foundationally change the way we model weather, predict climate patterns, and even revolutionize the way we desalinate water. So how exactly does this work and what does it mean for the future? Let's figure this out together. I'm Ricky, and this is Tube at Da Vinci. This video is sponsored by 10. Let's start with the basics. You probably remember from school that evaporation is all about heat. When you heat water, the molecules start moving faster and faster. Eventually, some of them gain enough energy to break free from the surface and become water vapor. This is why puddles eventually dry out and clothes dry on a clothesline. The process of evaporation also sucks up heat, which is how sweat cools us down. Now, here's where things get interesting. MIT researchers made a discovery. They found that light can directly cause water to evaporate without the need for heat. This is a huge deal. The MIT team made very precise measurements and has more than a dozen key pieces of experimental evidence to support their claims. And honestly, after review, I couldn't really poke any holes in their reasoning. It's similar to the photoelectric effect, which is how Einstein explained how light can knock electrons off of metal surfaces. The researchers measured evaporation rates under optimal conditions that were up to 4 times higher than the thermal limit. Now, the thermal limit is the highest possible amount of evaporation that can take place for a given input of heat, based on the basic physical principles such as the conservation of energy. And that limit is 1.4 kilograms of water per m²H. For the photomolecular effect, experimental evaporation rates were 4 to 7 kilograms. That means light can evaporate water much faster than heat alone. And this completely is counterintuitive and seems to break the laws of thermodynamics. But don't worry, we'll address that in a moment. Now, these moments are actually pretty rare in engineering and science, but this might just be a true eureka moment. But first, let's explore some of the implications of this discovery. The photomolecular effect has the potential to completely change the understanding of the world's water cycle. If light can evaporate water faster than we thought, that would have a huge impact on everything from cloud formation to rainfall patterns. And think about this, the photomolecular effect is similar to the photoelectric effect. Understanding the photoelectric effect led to the development of countless technologies that we rely on every day. Things like light sensors, digital cameras, laser printers, LEDs, and solar panels. So what new wonders will understanding and controlling the photomolecular effect bring? And this might be the most amazing part about this story. The potential applications for this discovery are mind-boggling. Imagine desalination plants that use light instead of heat to purify seawater. We can make clean water more accessible and affordable. Drying consumes 20% of all industrial energy use. Picture industrial dryers that work in a fraction of the time, saving energy and resources. Even our everyday lives would be transformed with light-powered dryers for our laundry and dishes. And then surprisingly, there's even new cooling systems for our homes, but we'll get back to that in a minute. Let's start with light-powered desalination. When you hear about solar desalination, this is probably what you picture. This is called photothermal desalination, and it turns light into heat, which then evaporates the water. But with a photomolecular effect, we can do things a little bit differently. We can use light directly to evaporate water without needing to heat it up first. This would solve several problems with traditional desalination, like losing energy as heat to the environment and the fouling of absorbent surfaces with water and other contamination. At least that's what these researchers are pointing at. The pursuit of knowledge truly is amazing, and you never know where new learning may lead. I learned to be a software engineer 10 years ago, and it changed my life, allowing me to save enough money to go full-time on YouTube. Plus, I got to work from home, travel, and spend more time with my family. And starting salaries for software engineers after graduation from tech boot camps is about $70,000 to $80,000. Like our sponsor this week, 10, the online learning platform that helps you land a job in tech. Try taking the career consultation with a 10 advisor. It's absolutely free and a great opportunity to talk with a professional about your future career. 87% of Triple 10 grads land a job in tech in the first 6 months, and they even have a money-back guarantee. Whether it's software development, quality assurance, or data science, Triple 10's externships allow you to work on real-world tasks with their partner companies and get live feedback. With flexible payment options and the ability to learn at your own pace, it's never been easier to build your tech portfolio with one of the best coding boot camps. And with more and more smart devices, the tech sector is only getting bigger. Check out Triple 10 using my link in the description below and save 30% on all their programs. Huge thanks to Triple 10 and you. Now back to the show. But there is something about this that's been bothering me and I had to look into it. If light has a certain amount of energy in it and you need a certain amount of energy to evaporate water, how can we evaporate 4 times more water with light than with the same amount of energy supplied as heat? Isn't this breaking the laws of thermodynamics? Where is this extra energy coming from? Well, it turns out the answer lies in this. It doesn't cleave off one molecule at a time, but entire clusters of water molecules. Each water molecule in liquid water is tied to 4 other water molecules through hydrogen bonds. To evaporate a single water molecule from a bulk of water, we have to cut, on average, 2 hydrogen bonds per molecule because each bond we break disconnects 2 water molecules. That's the amount of energy that we have to supply as heat because the heat releases individual molecules. But in the photomolecular effect, since photons of light are knocking out entire clusters of molecules, we only have to input the energy to cleave the outermost hydrogen bonds that tie the clusters of the bulk of water. So that takes less energy. It's kind of brilliant. But to get water vapor, you still need to cut those other strings loose. So where does the energy to do that come from? First, let's see how we would actually build a machine that works on this principle. What would it look like? I dove deep into both the articles from the team at MIT to find out. They don't describe it, but we can make an educated guess based on their result. The effect depends on the wavelength of light, and it's optimal at 520 nanometers, which is green light. It's also much more efficient when the light is polarized. This means that all the photons, magnetic and electric fields oscillate in the same plane. The angle also matters, and the highest evaporation rates come from an angle of 45 degrees with respect to the water's surface. So let's put all this into practice. We need a source of green light, ideally emitting at or near 520 nanometers. We could use green LEDs or even some type of green diode laser. We could also filter out green light from sunlight, but that's not a good idea because we'd lose the rest of the light, which is also energy that we couldn't harness. Next, we need to polarize the light to make it transverse magnetic or TM polarized. And this is where things get a little bit more tricky. If we use a regular light source and run it through a linear polarizer, we'd immediately lose 50% of the light in an ideal case, and obviously that wouldn't be the answer. But I found some clever workarounds. If we use laser diodes, there's no problem because they naturally emit polarized light. But lasers are also really inefficient, usually only around 30%. 50% for very expensive diode lasers, and a maximum of 65% under very specific and ideal conditions. Another trick is to use a special kind of birefringent crystal that splits the light into 2 polarized beams. One in the direction you want, 50% of the light, and one at a 90-degree angle, the other 50%. If we run one of the beams through a device called a Faraday rotator, we could twist one of the beams by 90% and recombine them, getting a single polarized beam with minimal losses. At least that's what I think we could do based on my reading so far. There will be losses due to scattering and absorption, but not as much as 50%, so pretty cool, right? Now for the water. We need to maximize the surface area exposed to the light. We could use thin films of water or maybe even tiny droplets. And then we need to control the temperature and airflow to make sure that the evaporated water is carried away efficiently. So would this actually work? Would it be more efficient than other forms of desalination that we already have? Well, based on my research, it definitely seems possible. However, current desalination technologies only reach about 7 to 16% of their thermodynamic limit. With the photomolecular effect, we could potentially blow way past that limit. But there's more. Remember how I said earlier that we'd explain where the extra energy comes from to break up those water clusters? Well, it comes out of the surrounding air. When the light knocks out clusters of water molecules, they collide with air molecules. These collisions break the clusters apart into individual water molecules, and in the process, the air loses some of its heat. So not only does the photomolecular effect evaporate water faster, but it also cools down the air around it. This opens up a whole new world of possibilities for light-based cooling technologies. Imagine air conditioners that use light instead of refrigerant, or even wearable cooling devices that keep you comfortable all day long, even on a hot day. The possibilities, again, are endless. But all that so far is based on products that we can build here on Earth. This actually extends much further, in fact, much further into the sky. For decades, scientists have been puzzled by a strange phenomenon. Clouds and fog seem to absorb more sunlight than they should, based on our understanding of how water interacted with light. This has been a major source of uncertainty in climate models. But the photomolecular effect could finally provide an answer. If light can directly break apart water clusters at the surface, it could also be happening within clouds and fog, leading to increased light absorption. And this could explain the mysterious discrepancy and help us refine our climate models. The photomolecular effect could be the missing piece of the puzzle. By incorporating this new understanding of evaporation into our models, we get a much clearer picture of what's actually going on in future models. One of the most interesting things about science is when we don't understand something, like you see an equation, you think, well, there's this piece missing, what could it be? And then we try to figure it out. And it's pretty rare when we do, and this might be one of those times. Just really amazing stuff. And it's not just science in the lab. The implications on products that we could all use in our day-to-day lives is kind of endless as well. Win-win. Really amazing. And as always, thank you for watching, and don't forget to hit like and subscribe because we have a ton of amazing engineering topics coming up here in the coming weeks. And until next week, I'm Ricky with Da Vinci. Thank you so much for watching.